Hello, everybody. My name is Juan Castano. I'm a civil engineering senior here in Ignis, and my presentation today will be about the Viaduct Cesar Gaviria Trujillo, which is a bridge in my hometown. I'll explain in a second. This bridge, it's located in the country of Colombia, which is located here in South America, and more specifically within Colombia, it's located in the city of Pereira. So it's actually in between two cities. So this bridge connects the two cities and crosses the Otun River. And this bridge solved a lot of problems because beforehand, if you wanted to go to one city to the other, you had to descend like this big slope right here, go all the way to the river, and then go back up to the other city. So that um, trip was a lot of traffic all the time, so it used to take like an hour. So now you just need to cross the bridge, and it decreased traffic a lot, and just times of commuting in general because it's two big cities. The one has 500,000 people, and the other one is a couple 100,000. So this bridge was built. The construction started in 1994, and it took 3 years to be built. So it was finished in 1997. It cost in total $60 million, which at the time, like it is a lot once you convert it to our local currency. And at the time that it was built, it was the 20th longest cable stayed bridge in the world, and it's one of the largest in South America still. So this is a picture whenever they were building it. So one very interesting thing whenever uh, cable stayed bridges are designed is that the engineer has to check the capacity of the bridge and the columns, like every um, part of the design, not only at service but also at the time that it's being built. So it's almost like a precast construction building, like that. That's how you think whenever you're designing it. So, like in every different stage, you need to make sure the bridge is not going to collapse because, yeah, like it's not going to be built from the in a couple of days. It took 3 years. So, yeah. So once the bridge was built, they did a lot of testing, of course. Like that's whenever every large scale bridge is built, they always put a lot of trucks. They usually fill them with gravel just to make sure the bridge is withstands the dead loads and live loads as specified. So this is a little illustration of how they did it and a few pictures of the actual trucks with the gravel. So it was all tested and it all works fine. So the geometric properties, this bridge has two lanes on each direction and also has a pedestrian sidewalk. And in total, it's 2,300 feet long, which is very, very long, but not everything is the cable stage part. So the longest span in between columns, it's almost 700 feet, which is um, this part right here. And then the whole cable stay portion is 1,443 feet. So from here all the way until here. So the tallest column, that is from the bottom where the ground is all the way to this top right here is 345 feet. So it's a very big bridge whenever you look at it in person. And also from the lowest point in the ground, which is where the river is at, all the way to the bridge is 180 feet. So it is, I guess, a quite intimidating bridge. Some people have like, yeah, jumped from the bridge and stuff. So they have a big old barriers nowadays. So hopefully people don't do that. And so structure wise, this bridge was built with concrete and with steel. So it's a hybrid construction. It has the big columns and like this part of the bridge is built all with concrete. So it's reinforced concrete and some pre-stressing post-tension concrete as well. And then the steel is all the girders and the deck part of the bridge. All the beams are made of steel, and all the cables are also made of steel. So in total, there was needed 25,000 cubic yards of concrete. So there was a lot of concrete used for this bridge, and also almost 3,000 tons of steel were needed to build this bridge. So all of this, the steel part of the bridge was built as elsewhere, and then it was just brought on site and then put with the cable stay part. So you put a section of the bridge, and then you put the cable on it, and then you start on both sides of the columns until you reach the other side of the bridge. So that's why it's so important to design it so that it can withstand whenever it's unbalanced. Because once if the bridge is together, you know the moments of both parts are balancing each other. So it helps a lot when it comes to how much weight and forces the columns need to resist. That whenever it's being built, it's not symmetrical, it's not equal. So you may run into problems if you don't take into consideration all the different stages of construction. So more about the structure. So this bridge was built in the 90s. So back then, the technology, I guess, wasn't as far as it is nowadays. So we can see that with the strength of the concrete was just regular 5,000 psi concrete. It's not things that you see nowadays in the skyscrapers that you can see up to 14,000 psi of strength of concrete, which is crazy whenever you compare it to 5,000. And the steel rebar inside the reinforced concrete was just regular 60 ksi rebar. Then the steel structure was actually grade 50, all the steel girders and all this part of the bridge. And then the low relaxation pre-stressed steel, the strands that were used for the pre-stressed steel was 178 ksi. So it's just as we learned in our pre-stress classes, the regular, nothing fancy was used for this bridge, just regular design. But it is pretty cool to see. It's an emblem of the city, I guess, of how large this bridge is. So whenever designing these type of bridges, it's very important to, as I mentioned a few times already, to check the capacity of the bridge components at every stage of the construction. You don't want to get focused on once it's on service or ultimate, because that's not all the different stresses that the bridge may have during construction. Is very, very important. A lot of the times where there is accidents on bridges, like whenever a bridge collapses, whenever it's being built, because sometimes designers don't take into consideration cantilever bridges whenever they're being built before it's supported on the hinge in the middle. They don't take into consideration that, so they may collapse, and that's very important. Also, whenever design it, bridge can be simply modeled as beams. So in this case, it was a continuous span beam, um, and it can easily be modeled like that whenever you're checking your structural analysis and stuff. In this case, of course, it has a big column, and it also has the cables. So that's all you thing to have into consideration, but it can be modeled pretty easily. Also, since it's a hybrid construction, the thermal deformation of steel is very, very important to have into consideration, because concrete doesn't have too much strain whenever there's thermal changes, but steel, on the other hand, expands a lot whenever it's very hot outside and it compresses. It becomes smaller whenever it's too cold outside. So that has to be taken into consideration. And another thing, very important, the place where this bridge was built, there's a lot of seismic activity. So that needs to be, of course, taken into consideration in such a big bridge. Although whenever the construction gets taller, wind starts being more important. Seismic in this level of activity, it's very important. So that needs to be checked. Actually, the bridge was finished in 1997, and in 1999 there was a big earthquake in the city. So they had to do some retrofitting and some repairs, because Although the bridge had was seismic resistant to some extent, there was still some damage whenever the big earthquake of 1999 happened. So since then, there hasn't been big earthquakes, so there hasn't been any problems. So these are just some things whenever engineers design big cable stay bridges that should be taken into consideration. So this is just a reference I use, which is some researchers in a university in Colombia about their seismic capacity of the bridge. And thank you very much, and hope you all enjoy the presentation.